Welcome to another lesson on parametric equations. In this video we will be looking at parametric equations, particularly that deal with our trig functions, so sine and cosine and tangent and stuff like that. And then we will be looking at how we can graph them. So just kind of like we did before, creating a table of values and then sketching what they look like. And then we'll look at one example, one application of parametric equations. All right, so let's do the kind of the same thing we did before. We're just going to create a table of values and then we'll sketch its graph and show its orientation on the graph. It's just this time we have trig functions. So x equals 2 cosine of t and y equals 6 sine of t. And since these are trig functions, we're going to go from 0 to 2 pi. We can do more points, but I'm just doing it by 90 degrees. So 0 to pi over 2 to pi and 3 pi over 2. I could do 2 pi. But 2 pi is going to be the same thing as 0. So I already know what 2 pi is going to look like. So if we take 0 and we plug it into cosine, cosine of 0 is 1. So 1 times 2 is 2. If we take the 0 and we put it in the sine, so sine of 0 is 0. 0 times 6 is still 0. If we repeat that process for the other three values of t, we get 4 points. So we have 2, 0. Here we have 2, 0, and then up to 0, 6, and down to negative 2, 0, back down to 0, 9, 0, negative 6. And if we did 2 pi, it would come back up to 2, 0. And so if we connect the dots, we get this ellipse. It's this elliptical shape here. And then again, noting the orientation, I started at 2, 0, and I'm going in this, this positive direction would be counterclockwise in this example. Let's try another one. So now we have x equals 8 cosine of 2t and y equals 6 sine of 4t, and we still want to go from 0 to 2 pi. The 2 and the 4 here are going to change the increments that we're going to need for our t values, just so we get enough data points. Because if I only did 0 and pi over 2, and then pi, so notice at 0 I get 0, 8, 0. At pi over 2 I get negative 8, 0. And at pi I get an 8, 0 again. So it would only give me 2 points on this graph. And clearly you can see there's more than 2 points. So sometimes with these trig functions, and even with non-trig functions, you're going to need to use more points. It just depends on the complexity of the graph. But in this example, I'm going by pi's over 8. So this is 0, 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, and onwards until I get to 8 pi over 8, which is pi. And I could keep going, but if I kept going all the way to, say, 2 pi, it'll actually repeat the graph. So going from 0 to 2 pi generates this graph twice. So anyway, we take the 0, plug it into our x function. Again, cosine of 0 is 1, so we're going to get an 8. Sine of 0 is 0, so we're going to get 0. And we continue working all the way through this. If we did pi over 8, 2 times pi over 8 would be pi over 4, and cosine of pi over 4 is root 2 over 2. Times an 8 gives us 4 root 2, and that's about 5.7. If we take pi over 8 and we put it in for the sine here, 4 times pi over 8 becomes pi over 2. Sine of pi over 2 is a 1, and so that's why we get a 6 here. So if we do go through and we do all these points and plot them out, this is sort of the shape of the graph we get, and it starts here at the 8, 0, and it starts in sort of this counterclockwise direction, but then it flips down to the bottom. It's almost like a bow tie here or an infinity symbol. So we have to put several arrows in here to show this is the direction, so it doesn't come up and hit the origin and then bounce back up to the top. It's going to go through the origin and loop, so it's making kind of a figure 8. And again, the graph would probably be better filled out if I used more points, but this is as many as we needed to get the general shape of the graph. All right, so let's look at eliminating the parameter. So we did this again in our previous example. In the previous example, we would take one equation, so maybe the x equation, solve it for t, plug it into the y equation, okay? We don't want to do that this time, though, because if we do that with these, we're going to have inverse trig functions. And And if you remember, our inverse trig functions have domain restrictions, and we just don't want to mess with that. So instead, we're going to use our Pythagorean identities. Okay. So if this, if you remember, the Pythagorean identity is sine squared plus, well, one of them anyway, sine squared plus cosine squared is equal to 1. So if I could take these two equations and solve them for sine and cosine, which I can just do by dividing the 3's, I can now take x over 3 and replace it for the cosine, and I can take the y over 3 and replace it for the sine. So that gives me y over 3 squared plus x over 3 squared has to still equal 1, because that's based off of this Pythagorean identity. And if I simplify that a little bit, I get y squared over 9 plus x squared over 9 equals 1. I could multiply the 9 throughout. We get x squared plus y squared equals 9, and that is a circle of radius 3 that is centered at the origin. Okay, so that's how we can eliminate the parameter using the Pythagorean identity when we have our trig functions. The second example, again, we have secant and tangent, so it's a little different, but we do have a Pythagorean identity for secant and tangent. It's tangent squared plus 1 is equal to secant squared. So if I can take the x equation and solve it for secant, and I can take the y equation and solve it for tangent, then I can plug those into my Pythagorean equation here. And so if we simplify a little bit, we get
y plus 3 quantity squared divided by 16 plus 1 is equal to x minus 2 quantity squared divided by 16.
So I'm going to take one more step and simplify this. I'm going to isolate the 1, and we'll see this actually when we get to conic sections later. But so if I rewrote this,
I would get x minus 2 quantity squared over 16 minus y plus 3 quantity squared over 16 is equal to 1.
This represents a hyperbola, which we haven't learned about, but we will. It's a hyperbola centered at 2, negative 3. All right, let's look at a couple more examples. In this first example, we have x equals 9 cosine of 2t plus 3 and y equals 4 sine of 2t minus 1. Notice they both have a 2t in them. And when we're dealing with 2t, we can still use, since they both have 2t, we can still use the Pythagorean identity. But now the 2t is what's going to be our theta. So we can still do the same thing. Solve both of these for cosine and sine. Plug it into your Pythagorean identity. And so we're going to get x minus 3 quantity squared over 81 plus y plus 1 squared over 16 is equal to 1. And again, we haven't talked about this yet, but this is an ellipse. And it's centered at the point 3, negative 1. And we'll talk more about ellipses in another week or two. If we do the second equation, x equals cosine of t and y equals sine of t, or sine squared of t, again, we're going to go back to our sine squared plus cosine squared t equals 1 equation. This time, sine squared is already y, so I'm not going to have y squared, it's just y, because that's what the original equation said. But x was cosine, so I'm going to have an x squared. So we get y equals x squared plus 1. If we solve that for y, we'd get y equals 1 minus x squared, which you should recognize that as a parabola. It opens downwards, and its y-intercept is at 0, 1. All right, if you want for some practice, you could take a look at page 45, specifically numbers 5 through 8. All right, and it's just for an application that we could look at, path of a projectile is a common application of parametric equations. We've already seen this with our satellite, but so we're going to have a function of x and a function of y. And this comes out of some of the physics involved with parametric equations, but if we have some sort of an initial velocity, so say we throw a rock or say we throw a ball at 10 miles per hour or 20 meters per second or something like that. So if we throw a ball and we have an initial velocity, and say we throw it at some angle relative to the ground. So say we throw a ball at 20 miles per hour and at an angle, an upwards angle of degrees. Okay, so we could figure out what this v sub 0 cosine of t expression is, and then it would just, x would just be a function of t. And so in a similar sense, we could do the same thing with y. So the y coordinate would have a negative 16t squared, and this comes out of gravity. If you take a physics class, you'll learn a little bit more about that. And then we have the initial velocity times the sine of our angle. So this will all just be a number here, times t, plus some initial height. So say you throw it and you release the ball 5 feet above the ground. So with these two equations, the x equation tells us how far horizontally along the ground the ball has traveled, and the y equation tells us the vertical distance. It tells us how high the ball is located. Okay, so we have a horizontal distance and we have a vertical position for our projectile. Okay, so let's take a look at an example. So say we're at a golf driving range. And in this example, we're talking about one that's a double decker. So there's 2 floors of this driving range. There's people on the ground floor, and then there's people upstairs on a second floor, and they're all hitting golf balls out into a driving range. So say at one point we have a golfer who hits the ball with an initial speed of 165 feet per second with an angle of elevation of 32 degrees. And because he's up on the second floor, the height of the ball initially is 12 feet. So what we want to do is we just want to simply write out what the parametric equations look like. So we're going to take the 165, that's my initial velocity, that's the v sub 0. We have the 32 degrees, that's theta. And then we have the 12 feet, which is going to be my h sub 0. So the x equation is going to be 165 cosine of 32 degrees. And all of that times t. And again, we could compute that on a calculator and see what that is as a decimal. And then our y function, y would be a negative 16t squared plus 165. That should be sine of 32 degrees. Again, all that's a number there, so it's times t and then plus 12. All right, so the next question, so we have our equations, and we now want to figure out how far does the ball travel. Okay, when this golfer hits the ball, how far will the ball travel? So one way we could think about that is when will it hit the ground? Okay, so the question when will it hit the ground is asking the question when is y equal to 0? So we're assuming 0 is no vertical height, so that's ground level. So when is y equals 0? So that means we're going to take the y equation and we're going to plug 0 in for y. Now, you might notice that this is a quadratic equation. So it's a t squared, a t, and then just a constant. So the a value is a negative 16. The b value is the 165 sine of 32 degrees. And then the c value is 12. So to solve this equation, the 2 main ways you could try this is either doing the quadratic formula. So again, A, B, and C. Or you could use the solver on your calculator, and that would be the easiest option. So if we went ahead and solved it, we're going to get 2 answers. We're going to get t equals a negative 0.134, and then we get 5.599. Now, again, t is thinking of t as time, so it's a stopwatch. So we're going to start at 0. So we don't really need the negative number. That would actually tell us if the ball went backwards when it would hit the ground, and that's not going to happen. So we know it's going to take 5.599 seconds, or if we round it to just 5.6 seconds. That's how long the ball is going to be in the air before it hits the ground, before it bounces that first time. So that answers the first question, when will it hit the ground? The second question is how far. So we take that 5.6 seconds, or 5.599, and we plug it into the t of the x equation, and we can figure out the x value is 783.5 feet. Again, that's just a straight plug and chug computation. All right, the last question we want to know is what is the maximum height and when is it reached? So the maximum height is y. It's reached when, and that's a t value. So to find max height, remember this is a quadratic equation, so we're actually going to find when first. We know the x coordinate, or in this case t, because it's a function of t, is negative b over 2a. That's the vertex location. So if we plug in the 165 sine of 32 over the negative 2 times the negative 16, we'll get 2.7 seconds. We take that 2.7 seconds, that's when. We take that and we plug it into the y equation, and this is just a straight plug and chug. We compute that and we'll get 131.5 feet.